morning everybody. So far we are talking about the coordination equilibria. So there we see that how a particular metal ion center is important of certain oxidation state, whether it is present in a catalytic site or in some biochemical reactions, and we are talking about the binding of so many ligand centers. So, if the center is present in a octahedral geometry and if we can block all the positions through the corresponding equilibria, and if 5 positions are occupied already, so we have 5 k values such as k 1, k 2, k 3, k 4 and k 5. And last one we will be talking about is very important in terms of the corresponding form in the biology what we get as in deoxymyoglobin. Another form is the corresponding oxymyoglobin, where we can consider simply the binding of the dioxygen molecule to that iron center. So, all these things are very important in terms of the corresponding coordination, bonding and the interaction to the metal ion center with these ligands. So, what we find in case of myoglobin, this particular part is a very important ligand system which we all know as a macrocyclic ligand, which is a porphyrin ligand, and this part is coming from the protein chain which is the globin chain. So, situation is much more complex with respect to the corresponding metal ion coordination when we finally talk about this OO coordination to this particular one. And apart from that, if we go from myoglobin to hemoglobin, which itself is a tetramer, so for such O2 binding we have to consider, and there lies the importance or the complexity in the biochemical reactions, where in the protein chain, so we can have a corresponding tetrameric form of myoglobin which is hemoglobin, and you still have available one coordination site to each iron center, and the binding of this O2 is again dependent on several equilibria, and that equilibria will again controlled by the different values like k 1, k 2, k 3, k 4. So, these knowledge are important, and we will find that if we have some k value, the formation constant value, how this can be energetically favored for the formation of this particular one. That means, the binding of the corresponding protein chain or the porphyrin ring to the metal ion center is again will be controlled by these Ka values. And in the simplest form, what we are just considering, that if we take a metal ion, say nickel 2 plus in a test tube in a solution, it is bound by the water molecules, then we add the sufficient drops of ammonia, aqueous ammonia, we will see the color change. And then if we add ethylene diamine, so what are the steps which are going on or taking place during this particular transformation is again controlled by the different Ka values, because if we consider that replacement of all 6 water molecules which were originally surrounding the nickel 2 plus center in octahedral geometry will now be substituted by 3 ethylene diamine molecules, because these ethylene diamine molecules are bidentate in nature. So, we need 3 of them. So, from this reaction, from the left hand side we have one cationic species which is the hexamine nickel 2 plus ion, which is binding with 3 ethylene diamine molecules. So, altogether we are considering 4 species, but on the right hand side we have one the complex species and the 6 ammonia molecules are coming out. So, this is the main idea. If a polydentate ligand such as a polydentate ligand or a multidentate ligand like EDTA, we know that it is a hexadentate ligand. If we give EDTA over here, so EDTA will also bind over there and remove all these groups. But for EDTA on the left hand side we will be having that particular cationic complex and the ligand as the EDTA. So, 2 species going to 7 species. So, the number of species which is coming out from the reaction is more. So, that must have some contribution to the Kf value, the equilibrium constant value, depending upon the number of species which is reacting. If it is ethylene diamine, we require 3 in the denominator, and if it is EDTA, we require 1. So, this Kf value is basically is changing, and this change is very important when we consider that one ligand is replaced by the other, such that initially we have the water molecules bound to the nickel, and then we add ammonia. So, ammonia is replacing all the water molecules. Now, ethylene diamine or any other chelating ligand will be replacing this particular group, and its important contribution in terms of the thermodynamic parameter is that the delta H values will also contribute, and as well as the entropy function will also contribute in terms of the number of molecules moving over there. So, the entropy is increasing from left to right. So, that will have the contribution for the formation of this particular metal chelate. So, then we just switch on to a particular theory which we will consider about the valence bond theory. And this valence bond theory, what we consider, because when we have this particular complex and we try to consider what are the orbitals available and the number of unpaired electrons. That means, we are focusing our attention not only to the number of unpaired electrons, but also the color. So, color we all know that how these can be achieved if we have two energy levels, one is E1 and another is E2, and there is an electronic transition from one particular level to other level due to the absorption of H nu, and that H nu will have some relationship with the corresponding lambda value. So, the one lambda will be absorbed. So, we will have the absorbed lambda, and we see the corresponding complementary color. This is the very simplest form or the simplest idea to have the color for these coordination compounds. So, these coordination compounds how they look like, that means the corresponding geometry we are talking now, how the different number of electrons will be there in the different orbitals. If we now consider the d orbitals and their arrangement in space, we will find that one particular theory which is talking about the valence and the structure, and this valence bond theory which considers that the overlapping of atomic orbitals. Why we are talking about these atomic orbitals of the participating atoms form a chemical bond, because they form a particular chemical bond. So, the orbitals available from the metal ion as well as the orbitals available from the ligand system is basically coming for the corresponding picture, where we get that the participating atoms, that means the metal ion and the ligand, is responsible for the formation of the coordinate bond. But this particular theory, this valence bond theory, will be talking about something where the field orbital of the ligand. We will now talk not in terms of the corresponding covalent bond, but the formation of the coordinate bond. So, the overlap is important. So, the valence of this particular or the valence electron configuration of the complex is important if we consider the overlap between a field orbital and an empty orbital on the metal ion. So, this picture will propose something about the geometry of the complex, and we can have the corresponding hybridization scheme. So, it is a very simple idea that how we consider the corresponding hybridization scheme for the methane formation or any organic molecule formation. We know that the CH4, how we can propose that for the formation of that CH4 molecule in terms of the hybridization of that particular carbon center. Similarly, that very basic idea will introduced for hybridization using the metal ion. So, metal ion will have now large number of orbitals, mostly the d orbitals if we talk in terms of the corresponding d electrons in all the available d orbitals. So, we must have some suitable hybridization scheme to understand the structure, because all these hybridization schemes we know that they will provide to ultimately that corresponding structure. So, as for the methane molecule, where we see that the hybridization scheme is sp3, and it gives rise to the corresponding tetrahedral geometry which is centered around the carbon center. or the carbon atom. So, now if we just extend that idea to any other metal ion, and metal ion is considering for the corresponding tetrahedral geometry. So, we can have the similar type of arrangement of the orbitals and the hybridization. So, what are the positioning of the different hybrid orbitals when they undergo overlap? So, this particular one, so atomic orbitals we can have, and if they have some proper character for bonding is called the hybridization. So, same hybridization scheme will be utilized for the bonding between metal and the ligand, that means the metal ion and the ligand. So, if we have a very simple thing, that means the tetrahedral geometry, and that tetrahedral geometry will give us a corresponding compound which is COCl4 2 minus, where we can have 3 unpaired electron, and whether that particular arrangement can give rise to a paramagnetic system or not. And is known that if you have a corresponding COCl4 2 minus species, it will definitely have unpaired electrons, it will be paramagnetic and will be attracted by the magnet. So, what we see there, that this particular arrangement, as well as we will see immediately some other species. So, one is the corresponding COCl4, and we can also go like species like COF3 3 minus and COCl6 3 minus. So, in all these cases what we see, we are talking about some interaction where the cobalt center is present, it can be 2 plus or 3 plus, and the ligands are chloride, fluoride and cyanide. So, what we find that this particular one, since we are talking about the 4 chloride groups surrounding this cobalt center, so the arrangement of this will be definitely a tetrahedral one. So, that tetrahedral geometry will give us something where we find that the cobalt is at the center of the tetrahedron and 4 chlorides surrounding this particular cobalt center. So, we will have this, so we have to give certain hybridization scheme or allow certain hybridization scheme such that in a tetrahedral arrangement we have this corresponding hybridized orbitals. So, these are the hybridized orbitals, so the bigger lobes which are pointed towards the corner of a regular tetrahedron. So, that is the basic idea. So, these are the typical sp3 hybrid orbitals. But when we talk about in terms of the corresponding unpaired electron on the cobalt center, what we see that we are not involving any hybridization involving the d orbitals, that means the d orbitals will be untouched. So, untouched d orbitals will have the same magnetic moment pattern what we can have if we have 5 d levels which are there and which are degenerate in nature. That means, all of them have the same energy. So, the n number of electrons which is present on cobalt 2 plus can be distributed on the 5 levels or the 5 orbitals which are d in character. But the situation is not so simple, because we can have 5 different d orbitals and which will be interacting differently with those ligands for this particular metal ion center. So, if we have something, so the hybridization scheme is telling us that this is there and the ligand will come and ligand will overlap with all these orbitals, but the metal ion will have the corresponding d orbitals available. So, the magnetic moment or the color of this thing can be explained in terms of the only the number of d electrons present in it. So, like that of our methane molecule, we consider as a sp3 hybridized orbital which will be tetrahedral in nature, and the number of electrons available for its magnetic moment will be present in the d orbitals in cobalt 2 plus. In case of nickel 2 plus, we will consider something else, because we have to arrange 4 cyanide groups, and we just now try to understand something where we find that changing from a ligand which is Cl minus to Cn minus is different. That we are seeing in this particular example, that if we can have a chloride, fluoride and cyanide. So, if we just consider the corresponding relative strength, that means how strongly they are interacting when we talk the corresponding interaction between the metal ion Mn plus with that of our ligand lone pairs. So, if the interaction is different, we can have a situation where the cobalt 2 center, this is cobalt 2. So, cobalt 2 center is interacting with 4 chloride ions, giving a particular magnetic moment. When we go to particular thing where we can have the COF6 minus, and if we just see that the number of unpaired electrons, if we get some indication what we get directly by measuring the magnetic moment. So, the magnetic moment will be there for something where we get the corresponding moment of the total number of unpaired electrons available in this particular species. So, here if the indication is that we can have 4 unpaired electrons, and those 4 unpaired electrons will give rise to a corresponding magnetic moment, and that magnetic moment will be considering for this particular arrangement, and this is octahedral in nature. So, the geometry for this will definitely because octahedron, because we can have the arrangement of 6 fluoride groups around the cobalt 3 plus center. So, this is cobalt 3. So, if this is sp3 for the tetrahedral arrangement, what we can have, we just include 2 of the orbitals which are of d character. So, 2d we can take. So, 4 plus 2, that means there we have the 4 hybrid orbitals, 4 plus 2 will give you the 6 hybrid orbitals. So, those 6 hybrid orbitals will be considering for the d2 and the other type of d2. So, there will be 2 d2 type things. So, one will be sp3 and another d2. So, we simply write something where sp3 d2. So, this d2 is we can have, and this d2 we are what we are getting, we consider as the d2 is coming from other type which is not outer orbital hybridization, and we can have 4 unpaired electrons. So, it is a different type of arrangement, but if we can go for d2 sp3, that means d from the 3d level, but these d's are from the 4d level. There is on the right hand side and those two will be on the left hand side. So, the situation will be different, and that we get for the next compound where we do not have any unpaired electron. So, unpaired electron number is 0, the species is diamagnetic, and this will give rise to d2 sp3 hybridization. So, that immediately tells us the nature of this ligand, and this ligand is completely different, because we are unable to explain the magnetic property of these two cases. In one case the number of unpaired electron is 0, and in another case number of unpaired electron will be 4. So, in this particular case we can have the 4 electrons are coming for these 5 d levels. So, these d levels which are 3d in nature, because we are not touching these d levels from this hybridization scheme. So, this will be there. So, we all know that it has 6 unpaired electrons. Trivalent cobalt is a 3d6 system. So, we put 6 electrons in all over these available orbitals. So, these available orbitals will give us 4 unpaired electrons. So, that is why we get a 4 unpaired electron for this particular species. But in case of this particular arrangement where the d2, so 2 of these d2 will not be available over there. So, we will have available only 3 d2 and 2 will go there, S and 3 p. So, 3 of them will be available for these 2, and this d2 sp3 will be there. So, this sp3. So, this is 1 d. So, you will have these 6 electrons will now be arranged in this fashion, and these are the corresponding one where we can have, this is not there. So, d2 sp3. So, 1 d, this is the second d, this is s p, sorry, this is there. So, sp3. So, this orbital, so will be therefore d2 sp3. So, this diamagnetic behavior can also be explained. So, this is a very simplest arrangement for where you can get that the magnetic property, and we will also try to explain in some cases what will be the color if we add chloride ligand, fluoride ligand or cyanide ligand to the cobalt solution, and what are the different colors we can get, and whether any electronic transition is possible from these levels. So, similarly, what we find for another example, which is bivalent nickel, which is diamagnetic. So, how we can explain the diamagnetic behavior of this tetracyanonickelate species, that we have to consider that we take out one d out of this configuration, which is 3d8. That means, we have 8 electrons to occupy the 4 available d levels on nickel. So, all will be paired. So, definitely this compound will be diamagnetic in nature. So, the hybridization scheme will typically will be DsP2. Similarly, for this one, that this particular Ag1 we have like that of acetylene. We know acetylene we have which is C2H2, the acetylene carbon will give rise to the corresponding hybridization is sp hybridization, and this particular one is a linear one. So, the linear arrangement for this will give rise to an situation where silver is at the center, and on the left we have one ammonia. So, nitrogen is bound to the silver and another nitrogen will be bound on the right hand side, and the nitrogen silver nitrogen bond angle will be 180 degree. So, this is the linear arrangement. So, the linear ligand arrangement will be like this. So, silver will be here and ammonia, this ammonia will be here and the second ammonia will be here, which will be for sp hybridized scheme. So, sp as well as sp3 hybridization scheme will be little bit simple, because we are not touching the corresponding arrangement of d electrons in the hybridized orbitals, whether it is same or different from the unhybridized electronic configuration of the corresponding metal ion. Such as this can also happen if we just simply go for the zinc. We know that zinc in the bivalent state, this is zinc in the bivalent state, where all the d orbitals are filled. We know that the electronic configuration is 3d10, and that electron configuration will give rise to some arrangement where we get that we all know that when we add gradually the hydroxide ion to a zinc 2 plus solution, initially there is a turbidity and then zinc hydroxide will be precipitated like aluminum hydroxide. But if we add more more hydroxide ion to this solution, so the precipitated zinc hydroxide will now be dissolved as more and more hydroxides will be bound to the same zinc center, giving ultimately to zinc OH whole 4 2 minus ion. And definitely this is a tetrahedral arrangement, because we cannot have the corresponding hybridization scheme what we just learned for the nickel as DsP2 hybridization, because the d orbitals will not be available for bonding for in the hybridization scheme. So, that hybridization will not be allowed to us for a typical arrangement where we get 4 ligands. So, this is one ligand. So, this is O1H, this is O1H and this is O1H, and these are the hybridized orbitals on the corresponding zinc center, and these lone pairs are coming from the hydroxide ion. So, this will be typically a tetrahedral arrangement. So, what we are trying to compare, that is whether we write in a circular form or the red arrow, that means we are not touching the corresponding electronic configuration of the free ion, that means the free zinc ion, while we get the corresponding complex species. So, nothing is changing, we are unable to change the color also, because these are all colorless, and we are not able to change the magnetic property, but here is no such clue for measuring the magnetic moment, because the zinc is filled. But whether this model is valid for zinc also, the valence bond picture is valid for the zinc also, that we can see. So, what are there? That means these levels are not filled. So, we have the empty orbitals. So, we require empty orbitals for the formation of the coordinate bond on the zinc 2 plus. So, these s and p orbitals will give rise to 4 hybridized orbitals on the 4 corners of a regular tetrahedron, and that regular tetrahedron will now be available for accepting the lone pair electron density from the 4 hydroxide ions. So, those 4 hydroxide ions will now give the corresponding electron density to the orbitals which are sp3 hybridized orbitals associated to the zinc center. That means, these are basically connecting to the zinc center, and as a result we have the zinc O bond. So, what we get? Ultimately we will be getting a zinc O bond. So, there will be 4 such zinc O bonds on the 4 corners of a regular tetrahedron. So, the valence bond picture we must have. So, which is also valid for a corresponding element which do not have any unpaired electron in the d levels. Okay. So, this we have seen just now that the square planar arrangement will give you a corresponding hybridized arrangement where we get a corresponding coordination which is dsp2. So, dsp2 hybridization is important for NiCN whole 4 2 minus ion. So, will be definitely a square planar arrangement. So, this particular arrangement what we get is the d for that particular arrangement is for the 3D level. So, out of these 5 or d orbitals, so we will see very shortly that what are the shapes of the different d orbitals which are also very important. So, that will also tell you that which particular d orbital will be available for this particular type of bonding. So, if this particular square plane is in the xy plane. So, those orbitals which are concentrated on the xy plane will be available for this particular type of bonding. So, what we do? We have 2 unpaired electron in the free ion situation, that means where we have the nickel 2 plus is present. So, this electron, this unpaired electron of the nickel will be pushed back to the orbital of the nickel which is 3D in character, pure 3D in character, making this orbital vacant for this hybridization which is dsp2. So, this orbital will be vacant and this vacant orbital will now accept the electron density from the cyanide ion. So, not only this, so we will have 1d, 1s and 2p now, not 3p, unlike we have the d2sp3 hybridization. In this particular case, we have 1d, 1s and 2p orbitals. So, they will hybridize together. Since we are talking about the orbitals which we will again see that what are the p orbitals also will be there. So, in this particular situations the dsp2 hybridization will be there and one p will be vacant and that p will not take part in this particular hybridization scheme. So, what we see there that this particular hybridization what we are considering as dsp2 hybridization, and we all see that the equi-energetic 5 d orbitals. So, these 5 d orbitals what we have and if they can have some level, we will talk about the corresponding shapes and all these things. So, the shapes of these will be there. So, we will start from here. So, it can have one orbital which is labeled as dx square minus y square. So, the electron density will be available for the orbital which centered on the nickel 2 plus will be in the xy plane. Then we can have another is dz square and then dxy, dxz and dyz. So, these are the possibilities basically. Likewise, what we know that for the p orbitals we can have the px, we can have the py and we can have the pj. So, what are the possibilities for this dsp2 hybridization which is labeled or tagged for a square planar arrangement? So, a square planar arrangement is there and we just take the corresponding plane which is the xy plane. So, if we just consider the xy plane, so we have the hybridized orbitals available over there and these hybridized orbitals will be pointing towards the 4 corners of the regular square plane. So, they are all dsp2 hybridized orbitals. So, this is along the pz direction. So, these two are x and y and z will be the perpendicular direction. So, we will just immediately for this. So, one of the p will not be there. So, this is out. So, this pz will not take part in this particular hybridization scheme and the corresponding one which will basically there. So, there will be 2 types of these orbitals in the xy plane for the d level. One is dxy and another is dx square minus y square. One will be pointing directly towards x and y and another will be in between. So, if our axis this is the x axis and if this is the y axis. So, is not this particular one. So, this perpendicular to. So, this is if this is the x axis and this is the y axis. So, definitely this particular orbital will be dx square minus y square. So, we will take this orbital. So, out of these 5 orbitals we take one of the d orbital, one S obviously will one S will be, and two P's will be Px and Py, giving rise to a corresponding dsp2 hybridization, which will be square planar in nature. So, that in detail the hybridization scheme will be 3D x square minus y square, then 4s and 4p2 which is x and y. So, if we take all these like this, so we will get, so the corresponding valence bond picture or the valence bond electronic configuration will be like this. So, these are the hybridized orbitals. So, definitely we will have the 4 ligands coming over here to accommodate the 4 lone pair of electrons on these hybridized orbitals. These hybridized orbitals will be empty, and we will have the 4 other orbitals available for accommodating the electrons, the 4 electrons which are for the nickel 2 plus. So, if we just take those electrons, so these will be filled over here. So, all 4 will be filled. So, we do not have any unpaired electron. So, the unpaired electron will be equal to 0 and we will have a diamagnetic situation. So, this we basically get. So, that picture is, if we just elaborate that way, so that will give rise to this particular arrangement. So, this is the corresponding hybrid orbital. So, the hybrid orbitals pointing towards all the corners of the 4 regular tetrahedrons. So, this is a typical geometry and the perspective what you can have. It is available everywhere. So, in this type of arrangement. So, these are the hybrid orbitals. So, these what are the shapes of these hybrid orbitals, that will tell us that why the tetracyanonickelate is diamagnetic and you do not have any magnetic moment for this. So, next we take another example where we take or where we add ammonia molecules as ligands to chromium 3 plus, and we are going towards the left, that is the lower side of the corresponding D series, where we have the chromium. So, titanium, vanadium and chromium. So, we all know that the D1, D2 and a D3 system. So, chromium which you get that corresponding 1. So, the number of unpaired electrons what we can is a D3 system. So, you have now if we can, so electrons available. So, 3 orbitals if we reserve or 3 preserve there for accommodating the electrons which are the chromium electrons, and we can take these 2. So, these 2 electrons again like that D2 will be the corresponding one for the D2sp3 hybridization. We have the dx square y square already we have seen just now, and other one will be dz square because it is a 3-dimensional structure. So, the ligands will be approaching in all 3 direction, all 3 Cartesian axes x, y and z. So, we have to take the dx square minus y square orbital as well as the dz square orbital for this hybridization scheme. So, these 2 orbitals we reserve for this hybridization scheme. So, these 2 will be there, and then we have the s and the p orbitals. So, p orbitals will definitely be x and y. We are not touching the z orbital, that is the pz in the case of dsp2, but here we have all 3. So, all 3 p we are taking. So, these 3 p orbitals we are taking for this particular arrangement. So, we will be having the d2sp3 configuration, and your magnetic moment what we expect for the free electron free ion configuration, which is the nickel 3 plus chromium 3 plus, that we have 3 electrons available on 3 orbitals, 3 available orbitals which is not changing due to complexation. So, we get that for this, and how we just consider these for the magnetic properties. So, because in all these cases we are just considering the corresponding magnetic moment, what we determine the corresponding mu b value, the Bohr magneton values we will be considering now, and we are talking about the number of unpaired electrons, whether you have a hybridization scheme of sp3 or a corresponding one just now we have seen as a d2sp2, and another one which is also of same type, that dsp2 we see that the corresponding 4 coordinate. So, 4 coordinate, that means the coordination number is equal to 4. So, another one we immediately write the hybridization scheme for the sp3 which is tetrahedral. So, you have the tetrahedral as well as the square planar arrangement for these, but we can have that another arrangement for the coordination number of 5. If you have the coordination number of 5, we know that the two regular geometry, one is the trigonal bipyramidal geometry and another is the square pyramidal geometry. So, depending upon the shape of these things, so this trigonal bipyramid is that you have a trigonal plane and a perpendicular one. So, what we take? We just basically take one more d orbital. So, one more d orbital we take over here for this trigonal bipyramidal arrangement, square pyramidal arrangement, but for the trigonal bipyramidal arrangement, if we move from here that dsp2, what we can do? We just do, here we have 4 hybrid orbitals. So, we can have one more hybrid orbital. So, what we do? If we just consider that it can be dsp2, obviously this is corresponding square planar one, but we are moving from a square planar one, but we are going to a trigonal planar one, which is we all know that we have a sp 2 arrangement. So, this sp 2 arrangement we can have. So, this sp 2 arrangement is a corresponding one for a regular trigonal plane. So, this regular trigonal plane we have. Now, we have to have some hybrid orbital which will be and these two perpendicular directions. So, these two perpendicular directions we can have. So, these two perpendicular direction L, 1 L, 3rd L, 4th L and the 5th L. So, this one perpendicular direction we can have this sp 2, we put what we have, we can put another p over there, that we all know that the p z was lying over there. So, we will take all 3 p. So, the hybridization will be dsp 3, which will be for your trigonal bipyramidal geometry. So, instead of taking the corresponding orbital which is the other one, that means the dz square, because we have not taking this one. So, this one will be the other one, that means since we are taking the pz orbital, this will not be x square minus y square like the case of dsp 2, this will be dz square. So, this orbital is also different. So, this dz square will be there and the pz. So, we are focusing our attention on the z direction because we are having 2 ligands on the z direction. And for square pyramidal arrangement, so you will have more d because we have a square planar arrangement, that means the dsp 2 arrangement, the square planar arrangement. So, the square planar arrangement plus 1 d. So, this will be dsp 2 for the square planar one plus 1 d we put, and we get the hybridization scheme as d2 sp 2. So, that is again this another second d will be where we are adding is our dz square now. So, these are the arrangements. So, this is typically all will be the corresponding mental model, how we look at the geometry and what are the shapes of the different orbitals and how these different orbitals will now take pair. So, as we move from here to up to the other two, that means the d2 sp 3 and sp 3 d2, the available orbitals, that means the orbitals which are available for the unpaired electron occupying the unpaired electron will be different. So, that will change the corresponding behavior of the magnetic moment, and this we measure experimentally. So, we do experiment. So, we use some balance which is known as the Goy balance, and if your sample, that means the most of the compound, the coordination compounds are solid in nature. So, the solid compounds we can put that balance and we measure the corresponding magnetic moment to understand about the corresponding magnetic moment. So, what we see this magnetic property is that the magnetic moment of the corresponding coordination compounds by measuring the corresponding magnetic susceptibility. That means, we have the chi g, the gram susceptibility, the gram magnetic susceptibility we can have, then we can convert it to molar magnetic susceptibility, and ultimately we can consider it as the corresponding magnetic moment. But the mu b what we report Earlier also we have seen that the mu b we can report in terms of the number of unpaired electron. So, whatever number of unpaired electron we can have on the d orbitals available, we will only focus our attention to those unpaired electrons, which will contribute to the overall magnetic moment of those compounds. So, again like that of fluoride and cyanide, because most of these cases we are just trying to compare, we are trying to see the corresponding strength of those ligands, whether your fluoride ligand is a stronger ligand than cyanide or the reverse is true. So, what we see here, simply by measuring the magnetic moment, whether your valence bond picture can give us some idea, but we are not getting right picture from the valence bond electron configuration. So, that is why we have to go from some other theory, and this is the corresponding limitation if we are not able to predict the corresponding right magnetic moment, which is experimentally determined quantity for all these compounds. So, in case of this Fe(6) 3 minus, it has a magnetic moment corresponding to 1 unpaired electron, while FeF6 3 minus has a paramagnetic moment of 5 unpaired electron. That means, the typical arrangements, though we are having the similar type of octahedral arrangement around the iron center, but our magnetic moments are different. That means, our hybridization schemes should be different. One will support the corresponding low spin arrangement and another will support the corresponding high spin arrangement, and we already seen that in one case the hybridization for the low spin will be d2sp3, less number of d electrons, d orbitals will be available for occupying those electrons, and for the high spin one more number of d levels will be available for those electrons. So, as a result, what we get, that is the corresponding deficiencies we can now jot down the deficiencies for this particular valence bond approach, because we will be having some other theory which is known as the crystal field theory, because the interaction we cannot explain in terms of the simple hybridization model like that of our formation of the methane molecule. So, that hybridization scheme is not applicable for this particular complexes, because it assumes that all the d orbitals are of equal energy, which is not true. We will see now that due to the interaction with the ligands, the energy of the d orbitals will change and we will have two different groups of those d orbitals, and arbitrarily we are using when we require we use, and when is not required we use the other one. That means, the use of these 3d and 4d orbitals of bonding is not so helpful, because the energy difference is pretty high, and this particular consideration of the energy difference between the 3d and 4d levels we are not considering. So, we are just having a model, mental model, where we are considering together for the outer orbital hybridization like that of our sp3d2, where we are considering these as the 4d levels, but the 4d levels energetically pretty high. So, though we are able to explain in terms of the corresponding magnetic moment, but it is not right to include the 4d levels for the hybridization. So, we will unable to explain the electronic and magnetic properties of these complexes nicely, because we are unable to predict the corresponding color of these complexes also. So, as we use for the main group elements starting from carbon to silicon, the transition metal chemistry will now be dominated by another theory, what will be known as the corresponding crystal field theory. And when the crystal field theory will have some limitation, will go beyond that and will be considering the molecular orbitals, where the individual orbitals or the atomic orbitals of the metal ion and the ligand will not give us all the explanations. We must consider the corresponding molecular orbitals, and this particular molecular orbital theory, the MOT we call it the molecular orbital theory, can sometime be known as also the corresponding ligand field theory, because the ligand like that of our crystal field. So, we are going slowly moving from crystal to ligand. So, is the interaction is like a crystal field interaction will be like the interaction of the sodium ion and the chloride ion, what we will be considering in this crystal field theory, but in case of the ligand field theory, we will be considering the interaction as the ligand field is responsible for the corresponding observation for the overall molecular orbitals for the metal and the ligand, that means the complexes. So, what we see that quantitative interpretation of the magnetic data is not possible to get. The color of the compounds are not precisely explained. So, these colors are very crucial sometime, that how we record these colors when we go for the corresponding spectrophotometric measurements, also the lambda max values and the epsilon max values. Then unable to also give the quantitative interpretation of the thermodynamic and the kinetic stabilities in terms of the corresponding valence bond picture, and is not possible for the exact prediction whether the complex will be a tetrahedral one or a square planar one in terms of only the magnetic moment. And lastly, it cannot distinguish the corresponding strength of the ligands, whether we have a weak field ligand or a strong field ligand, until and unless we use the weak field ligand for a type of complexes we will be knowing as the high spin complexes, and the strong field ligands will be for the low spin complexes. That we will discuss the corresponding strength of these ligand in terms of the corresponding d orbitals and how they look like along the different axes. So, if we just consider these orbitals in all these directions, and we will be considering these as just now we are leveling these, but now we see how they look like, how the dx square minus y square is different from the corresponding dxy, because the corresponding lobe, the availability of the electron density will be there in between the x and y axis. So, these two are in the plane, but they are somehow shifted towards say 90 degree on this particular plane. Similarly, in the same way that if we take other two Cartesian axes x and z and y z, we get these orbitals. So, we basically from the picture we just have some classification or the differences between the positioning of these when we place the ligand. Suppose we have a octahedral field. So, the crystal field or the ligand field is octahedral in geometry. So, which is very important. So, those ligands will be considering as point charges or point dipoles. If it is anionic, we consider as a point charge. If it is a dipole like water or ammonia, we have the corresponding point dipole, and we are not considering anything like that of our valence bond picture. That means, we are not considering any overlap. So, we just simply place these orbitals, that charges or the dipoles on x, on y and on z, on the positive side of x and y. Similarly, on the negative side of x and y and z, we will have, so 3 plus 3 6 will be there. Now, you see that those orbitals will be facing directly to those ligands are these two only, that dx square minus y square and dz square, because x, y, z they are facing these ligands. So, they will interact differently with that of our ligand system compared to dxy, dxz and dyz. So, basically we will be getting two groups of d orbitals in a octahedral crystal field. So, similarly, in any other crystal field, we have to critically consider the geometry. Even we can also think of the placing of s orbital and placing of p orbital within that particular octahedral field. So, placement of those orbital field and the shape of these particular orbitals, whether it is s, simply s, or px, py and pz, and as of the 5d orbital, we can have the different types of interactions. So, how the four lobes are interacting with the different orbitals. So, in case of dx y, dx z and y z, the four lobes are concentrated in between the coordinate axes. So, they will not be face to face there. So, they will not interact strongly as the lobes of dx square minus y square and dz square, which are along the x y axis, and they will be facing the orbitals directly. So, what we get that the combination of these. So, this basically what we see, that why this is different from that of our dx square minus y square, because these are all some amount of linear combinations. So, linear combinations of some of the orbitals. So, this is basically a hybrid of dz square minus dx square y square and dz square minus y square. So, these are the corresponding combination of these. That is why we get this particular one as dz square only, because we are omitting minus dx square and minus dy square. So, that is why this concentric lobe is there and is available in the xy plane. So, this particular one, truly speaking, it has to be written in this form, that means d2z square minus x square minus y square, but in the simplest way we are writing only dz square. So, if we place them in a typical octahedral field and the placement of these, so this will be there. So, they will basically of different types. So, we will have 5 orbitals will be there, and those 5 orbitals, when they are placed in presence of 6 ligands. So, we will be placing 6 ligands over there, and this is for the free ion. So, in this case the energy of the 5 d orbitals will be raised. So, the overall energy means that there is no such splitting or anything, but the overall energy of these orbitals will be raised. But afterwards what will happen? We will have 2 groups of these orbitals. So, one of these will be of 2 and another set will be of 3. So, they will be lowered in energy and we will have the corresponding barycenter. Because of the placement of these orbitals, they will not remain degenerate and this degeneracy will be lost, and the orbitals which are face to face, that means d x square minus y square and d z square orbitals will be raised in energy compared to the unsplitted energy level. This is the unsplitted energy level. We will be considering E for all the electrons. We will having this particular splitting. We will consider this splitting as x and the other splitting will be therefore the y. So, this will be the lowering in energy and this will be the elevation in the energy compared to the unsplitted level, which we get by raising the energy in the from the free ion situation. So, there will be the splitting. So, this particular one, since we have 3 d orbitals, we consider it as leveling as the T, which is a triplet one, and these are basically the symmetry level. Do not worry about these, and the other level will be the EG level, which is the doublet, because we will be having 2 orbitals. So, in a sense what we are thinking over here is that we are able to develop something, that means splitting is there, that means one energy level we have created and another energy level. So, the color, magnetic moment, everything can be explained nicely in terms of that. That means it is little bit superior compared to our valence bond picture. So, the crystal field picture or the crystal field theory which will apply will be little bit superior compared to our valence bond picture in identifying these. So, this particular EG level and the T2G level. So, EG set will be these 2 orbitals and the T2G set will be these. So, this can give rise to this particular one. So, we will just basically raise the thing. So, metal ion in an octahedral complex. So, we are simply talking about the field which is octahedral field, and that octahedral field will give rise to this particular splitting. So, one will be up by x from the corresponding free metal ion, then somewhere it is there the metal ion plus 6 ligands. So, it will be not directly from the free metal ion, but we will have the ligand just now what we have shown you, that it will be there. From there this particular splitting will take place. So, this particular one, so from there we will just get the corresponding splitting, and this x plus y, the whole splitting what we get as x plus y will be termed as the corresponding delta, and sometimes it is written as the delta O or oct. That means O subscript is for the octahedral symmetry. So, this is the corresponding crystal field splitting. So, since they are pointing directly towards the ligand, so their energy will be raised. So, this energy gap, this delta, which is very much useful, and the delta is very useful in considering the number of unpaired electrons and the energy transitions for the pushing the electron from the lower level to another other. So, this delta is the crystal field splitting, the delta O, the subscript O will be for the octahedral crystal field splitting. So, when we talk the corresponding absorption spectra, what color we should get, the absorption spectra will tell us that the crystal field splitting energy is dependent on the ligand's nature. That means the magnitude of this delta, how this delta is changing. So, definitely in all these cases, because we are bringing all the 6 ligands, whether it is a fluoride or chloride or cyanide, but we are bringing 3 different types of ligands surrounding a central metal ion, but the interaction will all be different depending upon the nature of the fluoride or the chloride or the cyanide. So, what we see that the delta will be changing. Just now what we have discussed in the very beginning of this class, that you have certain thing for the corresponding K values, the equilibria, the coordination equilibria. Now, the magnitude of that particular coordination equilibria will also be changing for the splitting. That means, the magnetic moment and the electron transition for electronic spectra will also be changing. And in terms of this delta value, we will immediately say a particular type of ligand can give you higher delta value compared to the other. So, when we have water molecule, when we have nickel 2 plus in solution, which will be replaced by ammonia in the first step, and those 6 ammonia what we have seen for the K values also, the thermodynamic parameters for that substitution also we have seen. But delta is a very simple parameter which can say that since we are able to replace water by ammonia and ammonia by ethylene diamine, so the delta value for En will be higher than that of ammonia and will be higher than that of your water molecule. And that we simply visually observe if we go to chemistry laboratory and we dissolve nickel 2 plus salt in a test tube, and which is the corresponding hexa-aqua complex, immediately we see the color which is green. Then we add 1 drop or 2 drops of ammonia. You never know whether all the water molecules you are substituted, but if you add little bit excess of ammonia, only little bit, we will be getting something which is blue in color. So, that blue color is due to the corresponding hexamine complex. And if we add now the ethylene diamine, which is a liquid, so ethylene diamine solution also drop by drop, which can be diluted one also, you will just see a blue to color change, a blue to violet coloration. That means, your ethylene diamine complex is pretty strong and the color is changing from green to blue to violet. That delta will also tell you how these different colors are changing, and the K values are saying that no, it will go from left to right, because the K value for ethylene diamine is much more compared to your corresponding K value for the hexa-aqua or hexaamine complex formation. So, this is the thing, that is the pictorial representation for these things. That means, what we get, we are having here. So, what is that is the your delta value. So, your splitting we all know now that the placement of 6 water molecules surrounding this nickel 2 plus center is something, and we have 2 unpaired electrons. So, definitely is a paramagnetic compound, and we can have this particular situation that the energy values. Now, we can start thinking how we get the color. So, what particular lambda value is absorbing and how this color is changing from green to blue and to violet, because your delta value is changing. It is small, it is medium, and it is higher. So, when the separation is higher, we have the violet coloration. So, what violet coloration we get for the corresponding lambda value, because the lambda for the corresponding complementary color. So, we should have the corresponding absorption. So, the absorption will be in the higher energy values, that means the shorter wavelength. So, the shorter wavelength absorption will take place in case of tris ethylene diamine complex compared to the corresponding hexa-aqua nickel 2 complex. So, that is why we get. So, we should be able to justify this particular color change in terms of the corresponding delta values. Why the color is changing from green to blue to violet? If we know the order, that means En is greater than NH3, NH3 will be greater than water in terms of the corresponding delta values, and if we just talk in terms of the corresponding delta 1, delta 2 and delta 3. So, delta 3 will be higher than delta 2 and delta 2 will be higher than delta 1. So, from this how we can apply these values and what will be the magnitude in terms of the pairing energy, we will all discuss this in our next class. Okay, thank you.